the spin type tip that there's been a lot of experience in fabricating. So if we have too much difficulty in producing a sharpened tip the way we want it with the reactive ion etch, we can just simply go back to the very successful spin type tip and add our gates on top of that and a collector. We see the future as being basically a VFET or a V2 FET computing capability that will be perfectly designed for high radiation, harsh environments, and broader temperature range requirements than we can currently meet with semiconductor devices. All of the conductors are metal within the device, and so there isn't the resistive heating that even occurs in a semiconductor version of a VFET. Also, we get bonus benefits, but I haven't even brought those up, about speed, which we expect to be dramatically faster than what's currently available. Cutoff frequencies for Jinhuan's early prototypes were 450 gigahertz. And we think we can do considerably better by focusing on reducing all the elements that contribute to that particular delay time. So I really believe that aerospace, outer space, and the nuclear environments are ideally suited to the capabilities of VFET and V2 FET transistors that we haven't seen possible before with typical semiconductors, which in a real sense are quite fragile when you think about it. In any case, thank you so much for your attention.
Lifetime. So you have exponential impacts on the work function and the electric field, and as you repeat issues of tip counting over time. Like the strange things that happen with the tips in this vacuum environment where there's some residual gas, and there's the impact of electrons, which you mentioned what energy the electrons would have on the impact.
Well, these particular, with the, let me go back to the, so this particular type of tip, which is what we would be using, whether it's a reactive ion etch or in this case the spin deposited tip. They have been testing and using these devices at much higher voltages, order of magnitude or two higher voltages than we would be using them, and they have seen lifetimes in excess of 10 years for this type of device with high voltage and high current. We expect to be using very low voltage, below 5 volts, possibly as low as 2 or less. We expect to be using very low current, and so it becomes an ultra-low power device that has very little chance of having any issues with deterioration by ionization of either the collector or the tip. Another question?
Yeah, so do you have any existing working devices, and if so, can you say something about the performance?
We're actually in the period where we're designing some circuits to be fabricated, and we're not actually at the point where we actually have our hands on some devices. We hope to have some devices fabricated potentially this summer, and then we'll be able to give some apple-to-apple comparisons and get some real characterization going. Nobody, until we came along, has showed any inclination since Ken Shoulders 60 years ago to do logic with this kind of device. So the developers of the spin field emission devices and arrays were pleasantly surprised when we told them we were proceeding to turn their beautiful work into tiny switches that would eventually be addressable logic elements. Go ahead.
Hi, the question is based on ultra low power capability of your device. So we can run at some threshold voltage. We can run an open source processor at 0.5 milliwatt with the RF design, the radio on it. Could you please compare similar designs with this technology? What would be the and we can run the some threshold designs at 330 kilohertz to 100 kilohertz. So the performance is reduced there.
Which kind of device is
It's a
that?
sub-threshold design of CMOS process.
Okay.
So we run at 0.5 volt supply voltage,
Yes.
and it runs at 30 to 100 kilohertz, and power consumption is 0.5 milliwatt.
Okay.
So how could you compare that design with this technology? Because you're claiming 400 gigahertz speed. So will there be a thermal design power issues? Like, could you please explain about the power aspect of this design?
Well, actually, the 450 gigahertz was produced by Jin Han's initial prototype in terms of a cutoff frequency. I believe that we will be able to go 2 volts and below eventually in terms of the bias that we need to put on the device. And a very much considerably lower gate voltage potentially. However, the actual bias voltage and the gate voltage range that we are operating in would be just for the convenience of the range of operability of the device. And so it's adjusted mainly for that particular consideration. The speed is just happens to be a benefit of not having resistive structures to work with, and the fact that we're using a vacuum as a conduit instead of a wire for the most part. But every other conductor in our version will be metallic, as are the spin devices typically today. I don't think we're going to get down to the millivolt level, but I think that's more a matter of design rather than potential. But I appreciate learning more about your device. I think it's very interesting.
Sure, it has its own restriction. It can be used in IoT applications. So when you move the same design to high performance computing, it will go to the range of watts, literally. Or GPUs are now taking 400 watts for one single core. So I think this comparing this method with high performance computing cores will be a very fast discussion. So I was curious how low we can go with the power. So it will be useful for future IoT systems.
I think eventually we'll be able to get a laptop supercomputer running at 10 watts with no excess heat and no downshifting of speed or failure for temperature considerations. I think that's going to be a huge element in being able to get people to be early adopters. Thank you.
So the focusing electrode, do you only need that if you stack up multiple gates, or why is that required?
Well, actually, the e-beam from the tip is fairly broadly spread, and when we want to get to the point of deflecting the beam to one side or another of a collector, so that we can take advantage of base 3 for quantum emulation, or just simply to develop computing with base 3, which has some significant, interesting considerations, as well as higher number base computing capability. I think in general, we will adopt it even to a simple triode, just simply because it focuses the electrons on the collector, and we don't have to worry about internal scattering. And I think that'll just simply give us the experience to continue forward. And so we'll go ahead and apply it to the most simple devices as well as the higher order gate devices down the road. In the back.
What's
it's very scalable. The particular device node that we're working with on these devices is a 40 nanometer by 40 nanometer unit cell, which is approximately 10 to 20 nanometer node. However, the initial devices that we're going to build are probably going to be between 130 to 300 nanometers, just simply because we're at the point where we want to characterize the device and get as much information as we can to tailor the structure to optimize performance and reliability. And uniformity is also a consideration. So there are a number of things that we're doing. What they also did with display devices based on the spin-type field emission array is they added a resistive layer so that the actual peak performers out of the device array didn't suck up all the current available from the emitter source. They added a resistive layer, as we've also done here below the emitter base is a silvery colored layer. That's a layer of resistive material to basically reduce the chance of having excess current flow to a single group of devices. But basically, we'll start with a much easier to construct resolution node level, so somewhere around 130 to 300. And then we'll bring it down to the node level that we have here, which we expect will interest NASA and DoD and aerospace applications for even lower power and considerably faster operating capability. Yes, in front. That's you.
Isn't the speed and power, looks like it will be limited by?
I suppose there's a possibility that the emitter power will be limited by interconnect, but the interconnect isn't any different than it would be on any other IC. And so certainly we can adjust for that. The size of the device will help determine what the amount of current that will be produced. So if we have a different size device, we can scale up the devices if we want to use them for a current generating or amplifying capability. So there's both that capability as well as having the very small digital switching capability. But basically, I believe we can pretty much adjust the current capability of the device over a broad range. Yes.
In terms of the radiation hardness, it seems like you mostly explored the total ionizing dose. Is there any expectation for the single event effects as to how good it performs?
My answer is this. Basically, I haven't tried the single event effect because there's like the heavy ion was not very available from NASA's perspective. So this is the reality. But in principle, actually, there's no materials being out by the radiation. So in principle, I wouldn't expect there's a single event effect in the vacuum channel. In theory, there's no material being ionized inside of the channel. But in practice, I haven't tested yet.
Okay.
We have that expectation as well. And we've even gone for a fully metallic device in the sense that all the components, the emitter, the gate, and the collector are all metals or metal alloys. We're not even using polysilicon or any dope material at this particular point. And that should be even more in our favor in terms of being essentially inherently immune to those radiation effects, even down to single event potentially. Any other questions? Well, thanks again for having us out.